So in the last example, example 4, we found out, ready, that the derivative of sine of x equals cosine of x. And we did that with some intuition, graphing the slopes of the function sine and realizing that the shape of that graph turned into a cosine. So because I'm looking at example 5 and it says use your calculator to sketch a graph of the derivative of y equals cosine of x, it says, can I identify my result? Well, I just happen out of the corner of my eye to have seen that down here, it actually tells me that I'm supposed to find negative x. So when I take the derivative of cosine, does it look like negative sine? So I want to go in here and actually try that. So here's my calculator, and I'm going to define a new function. And my new function, it looks like I had already previously defined it. So that's okay. I'm going to redefine it. How do I know that it had been previously defined? Because G is bold. So I'm going to redefine it, and I'm just going to call it cosine of x. And here's my deal. I always make sure that I hit that button. You can see it's highlighted in red. That's the button to actually get a trig function. For various reasons, sometimes when I try to type it in with the keys at the bottom, COS, for cosine, it doesn't always pop up as the trig function. I highly recommend using the button. I did forget, though, that what I was trying to do was take the derivative. So I'm going to go back, edit my line. On the menu button, I take calculus and derivative here, not just derivative at a point. And notice, oh, okay, so that's my cosine, and I wanted to throw it into that box so that it says, hey, take the derivative of cosine. And I'm noticing that when I just ask for a derivative, it wants to know what variable I'm using. I'm going to put that variable in. So this is a CAS function. You don't have to use this, in the AP exam, but it is kind of handy. So now I have defined G to be this function, and I'd like to take a look at the graph. So I'm going to go Control and Dock, and I'm going to add my graph, and I'm going to say then G of x. Please show me what that graph looks like. And I don't know about you, but that totally is clear to me that that is sine. That is that instead of going up and then coming back down and then going back up again, it goes down and then it comes up and then it hits back down at 0. So that clearly is the sine function. But just in case you weren't sure, you can hit that trig function, and let's pick sine, and let's make it negative in front, and let's say sine of x, and when I graph it, boom, it lays exactly on top. So I know for sure that I'm right and that Mr. Taylor is right, and we can now sketch this guy. And honestly, I like to sketch it, kind of just the positive part of it, because I know that sine usually starts like this, and I'm not going to do that, right? Instead, I'm going to go like this. So my result is negative sine of x. All right? Yay! So now we know those two derivatives. We're totally intending to use them during this section of the book, okay? Example 6 moves on. We have another family of equations that we'd like to become familiar with in this section. First was some trig, some sine, some cosine. Now we want to work with e to the x and the natural log of x. And we'd already worked with the natural log of x just a little bit in the previous video. So this one says use your calculator to graph y equals e to the x and its derivative in the same coordinate plane. And what do you notice? Now, this would have been a super fun activity to do in person, and I'm sorry that we can't do that, but here's basically what I'm saying. Ready? F of 1, let's have that be e to the x. There's the button that I'm pressing that gives me that constant e, and I'm going to type in the x for myself, and then I'm going to hit tab, and I'm going to get rid of this other function, and I want to define the derivative, and then I'm going to throw it in there. So I think it would be funny to use e, but I'm not gonna. Let's say I'm going to use m, and m, oh, actually we've been using that for slope. How about I use n? N of x, I would like to now define that to be my derivative, and here's, I'm going again to the menu button, calculus, and derivative, and I want to say d dx of, ready, e to the x. So there's e and to the x, and I hit enter, and that's awesome. Just in case you were wondering, the CAS function will tell me what my derivative is. Wait a minute, is it broken? It just gave me back the same thing. Nope, it turns out that's really the answer. If I throw in my, what variable did I use? I used n. When I throw in this function n of x, which is the derivative of e to the x, boom, I get that. Now, do I have another graph still up here? Sorry, I'm going to delete that graph so it stops distracting us. There we go. N of x is the derivative of the first function, and when I graph it, it turns out that the derivative of e to the x is e to the x. We just proved it. The calculator confirmed it by using that cute little computer algorithm that tells me the answer. It's kind of handy. So it says, what do I notice? I notice the graphs are the same. I notice the graphs are the same. And the reason for that, by the way, is that exponential functions are modeling the rate of change. That's literally what they do, is model the rate of change. And the instantaneous rate of change should therefore be the same as the original function. All right, so e is the only base for which the basic exponential function and its derivative are the same. If we change the base to anything else, we're going to have to add a constant, and you'll see it. All right, so when we move to differentiating more than just e to the x, I'll show you what that looks like. All right, but for now, we have this tool that we've sort of been investigating. We investigated it on our calculator that, hey, e to the x, when I take the derivative of it, I get e to the x. Down here for number 7, I wish this was all in one video because I had just gone over the graph of the natural log of x squared minus 3. So hopefully you're watching these videos one right after the other, and you remember me saying, the graph of the derivative looks suspiciously like 1 over x, but it's like a little bit moved around, right? With this investigation, we wanted to estimate some slopes. And I'm looking at the graph of y equals the natural log of x, and it's kind of hard to see on this picture. I hope you can see that purple line is the natural log of x. And since there's a bunch of lines here, it's very hard for me to sort of, mentally figure out what those slopes are. Say, for example, that I'm talking about at that point, that's a 1. That would be this point right here. It says fill in the table by estimating slopes at the points indicated with as much precision as possible. And we're trying to figure out the slope of the tangent line so we could estimate what do we think the derivative is. And I've already said what the derivative is. I did that on purpose. But let's see if we can see that pattern, okay? So I will mention that that green line is the tangent at 1. And I know how hard it is to see, so I promise we're only going to do one of these. Ready? I'm going up 1 over 1, up 1 over 1. And that must be my slope, up 1 over 1, okay? Now, what about the others? Well, the other ones, I'm actually going to cheat, and I'm going to ask my calculator to give me the values of those derivatives, okay? So here we go. I'm opening that up, and I'm going to type in here that I have the natural log, and I'm going to say, why don't we call it L of x? And I want to define that as the natural log function. And here I'm going to hit Control and then Enter on that button. That's how I get the natural log function. And in fact, I meant to actually make a derivative here. So I'm going to hit Menu, and I'm going to do Calculus, and I'm going to do the derivative. And oops, I'm going to put that natural log in there. And I'm sorry about that. I hope you guys do it by making your derivative show up first. There we go. So my L function is the derivative of the natural log function. Okay, great. Now my table asks me to find out what's happening at a half, what's happening at 2, what's happening at 4, and I'm trying to move it, there it is, what's happening at 6. So let's try that. L of 0.5, that's a half. L of 2, L of 4, and L of 6. Boy, I sure did recognize that pattern right away. Didn't I already say that it was going to be 1 over x? Wait a minute, that first one looks a little bit funny. 0.5, I got a 2. Well, that was weird. 2, I got a 1 over 2. 4, I got a 1 over 4. And 6, I got a 1 over 6. So, yeah, this one, let's quickly calculate it by hand just to confirm that that number really should be 2. And I'm also going to ask you, what do you think might happen at 1/3? Let me show you. If I say that this function, what I can see right here is that this is 1 over x, right? 1 over 2, 1 over 4, 1 over 6. That's got to be my derivative, meaning y prime is going to be 1 over x. So if that's true, what would happen if I plugged in a half? So y prime of 1/2 would end up being 1 divided by 1/2, which is the same thing as 1 divided by 1/2, which is the same thing as 1. Do you remember this little trick when you're dividing by a fraction? You're supposed to flip the fraction. That is how I end up with 1 times 2 over 1 is 2. And therefore, if he had asked you what happens at 1/3, you should get a 3. What happens at 10? I should get, 1 over 10? I should get 10. What happens if I put in 1 over 1,000? I should get 1,000. Okay? So hopefully now you can see that the derivative of the natural log of x is 1 over x. Awesome. Yes, my conclusion. Differentiating. Oh, here it is. He gave it to me. Okay? Let's highlight it. So now we are moving on in the section. I have these just a few problems which it says I want to do without using a calculator, okay? And I totally do want to do this without using a calculator. It's just that when I'm first looking at this first problem, I do need to rewrite y, because I would like to use the power rule. Y is equal to 2e to the x minus 3, the natural log of x, plus, ready, x to the 1/2 power. Don't forget how to take that derivative, okay? Y equals e to the x, the derivative of that. If I'm multiplying e to the x by 2, well, when I take the derivative, I will still have an e to the x multiplied by 2. How about the natural log of x? Well, I should end up with a 1 over x. So there's going to be a -3 times 1 over x. And yes, that does simplify into this -3 over x, but you don't have to put that, right? You're allowed to just substitute in the value for the natural log of x and leave it. And then when I take the derivative of x to the 1/2, I get 1/2 times x to the -1/2 power. And again, in the interests of space and time, I'm going to leave it like that. I'm not actually going to simplify it, okay? For number 9, we do need to be familiar with theta. Hopefully you remember that that means an angle that we don't know. So it's just like a variable x. In fact, I'll mention that if you change things to x's on your paper in the AP exam, they'll still grade it. They don't mind. They know that, theta isn't your favorite notation. It is literally Greek. Like when somebody says, hey, that's Greek to me, you're not kidding. In calculus, it actually is Greek. So if I take the derivative g prime of theta, if I accidentally wrote an x there, it would be okay. All right. The derivative of sine is cosine, and there was a 3 in front, so there should still be a 3 in front. The derivative of cosine is negative sine. And there was a -5 out in front, so there should still be a -5. be careful with your parentheses here. I am taking this and I'm making the derivative happen right there. But for clarity, it might be a good idea it might be a good idea for you to actually do 3 cosine of theta plus 5 sine of theta, okay? Because a negative times a negative, those should happen and become a positive. If you put the parentheses in the wrong place, somebody might think that there's a multiplier or an adder. We're not adding these two terms. We are trying to multiply this 5 times this negative sine of theta, and that 5 happened to already be negative, so a negative times a negative is what made that be positive. All right? Find the indicated value without using a calculator, and I have my h of x, and so h prime of x should be, ready, 15 cosine of x plus 4e to the x. And I believe right here that that's a typo. I'm pretty sure that's supposed to say h, okay? Find the derivative. But specifically, let's find the derivative at 0. So h prime of 0 is 15 times cosine of 0 plus 4e to the 0. And yes, this can be simplified further, but again, in the interests of time, I'm just going to leave it just like that. Now, wait a minute, Ms. Chatra, you still have a variable there. E is still there. No, don't forget. E is that number, 2.7 something, right? And so we leave that as exactly as it is. Get it? E for exactly. Just leave it. That's the exact answer. All right. If you feel like plugging it into a calculator, the calculator will tell you what that simplifies into. E to the 0, by the way, is just equal to 1. So I know we're going to get a pretty nice number here. In fact, I believe that the actual answer is going to be 19. But you go ahead and calculate it. All right. So for number 11, it says f of t equals 4 times the natural log of t minus 3e to the power of t. And this one, it actually wants me to do 2 derivatives. So that's fun. Here's my first derivative. F prime of t is going to be 4 over x, right? That 4 is a multiplier, and I have that 1 over x. And so if, in the interest of time, if I just want to go ahead and throw that together, then I can. And then I have a negative 3e to the t. Well, what if I take the derivative again? I kind of need the power rule here, so I want to rewrite this as 4 times t to the, that's supposed to be a t. 4 times t to the negative 1 power and minus a 3e to the t. That's something that I can use the power rule on. The second derivative will be, ready, a negative 1 times that 4. T goes down to the negative 2 power minus 3e to the t again. And if I want to plug in 5 here, what will I get? F prime of 5 will end up being, ready, negative 1 times 4 is negative 4. And then I have t to the negative 2 power. Well, t is supposed to be replaced with a 5. And I have negative 3e, again, with that 5. I kind of wish I'd done that in a pretty color. Here's pink, here's pink, here is pink. And is that my final answer? Sure. Why not? In the interest of time, you can leave it like that on the AP exam. Now, obviously, if you had a multiple choice question, you'd want to go all the way to the simplified answer. But in the interest of time, you might be picking other multiple choices to do first. Come back to this one, see if you can't suss out what the answer is if you do have enough time, okay? For number 12, it says find an equation of the line that's tangent to the graph of that when x equals pi over 4. And let's do that without a calculator. So you need to know what cosine of x is at pi over 4. And I'm mentioning this as a homework, so you can go in here and just real quick remind yourself, do you know what cosine of pi over 4 is? I'm going to plug in the cosine. You may have noticed that my trig functions have a tendency to just sort of wander across the page. There's something about the technology that I'm using here where it makes it do that. But I did know that the answer was the square root of 2 over 2, and you probably did too, right? So now that we have that, when x equals pi over 4, y equals the square root of 2 over 2. Okay, and so we can now go ahead and use that value. Oh, I'm sorry. It's a -3, right? It's a -3. That is not drawing well. Times the square root of 2 over 2. So what about the derivative then? Well, let's take the derivative. F prime of x should be -3 times the derivative of cosine, which happens to be a negative sine of x, which ends up being, ready, a +3 sine of x. And hey, I do need to evaluate this. I need to evaluate it at pi over 4. And I do have this one memorized. Sine of pi over 4 is also magically the square root of 2 over 2. So this will be a +3 times the square root of 2 over 2. And now I have everything I need to be able to fill in my equation, y minus y sub 1 equals m times x minus x sub 1. And that equation, I can use it in the following way. Ready? This was my slope. 3 times the square root of 2 over 2. This is the bones of my equation. And I found out that when x, oops, I meant to do that in pink, my computer. This is -3 times the square root of 2 over the square root of 2. That looks terrible. And an equal sign right here. And then minus, what was x originally given to me? It was pi over 4. Don't change any. Leave it just like that. You're ready to do the homework.